Morning everyone, welcome to this morning's GCSE Physics live group tutorial. The topic today is energy changes. This will be a 1 hour session, so we'll finish at 11:15. And this is GCSE Physics. As I said, lots of you will have joined us for our previous physics sessions, so you will have met our wonderful tutor, Preshayla. For those of you who haven't met Preshayla, she studies physics at Loughborough University, and this is her 4th year as a tutor. Should be a really good session today. Thank you for joining us. My name's Tilly, I work at my tutor, and any questions you might have for either myself or Preshayla, just put those in the chat or the Q&A. What we'll do is we'll keep an eye on the chat throughout the session. Also have some time for a Q&A session at the end, just to pick up any questions you might have missed along the way. So don't worry if your question doesn't get answered as soon as it's put in the chat. We'll make sure to get to it at the end. Just a reminder that you can access all the past physics tutorials on the My Tutor YouTube channel, and also some shorter videos where Preshayla's gone through some specific exam questions. So those should be really handy for you guys as another revision resource. I'll just wait a couple of moments as some other people join. Brilliant, okay. Preshayla, are you all good to go?
Yeah, all ready.
Great, have a good session, guys.
Okay, so what we're going to be covering today is energy changes. So we're going to learn about the energy changes that are involved in heating a material. And then we're going to be talking a little bit about power and how power is the rate of energy transfer. And then we're going to go through the required practical. Okay, so first of all, heating. I'll summarise yesterday's webinar first. So if you weren't there yesterday, or if you just do want a refresher, yesterday we went through energy stores. So we went through the different types of energy stores, and there were 8. So magnetic, thermal, chemical, kinetic, electrostatic, elastic, gravitational, and nuclear. So we need to know what they are, where they're found, and in what kind of applications do we find them. And then we went through some common scenarios, which include energy transfers. So, for example, a kettle boiling or an object being thrown, and energy changes that happen in each. Then lastly, we went through 3 new equations for kinetic energy, elastic energy, and gravitational potential energy. Okay, so heating materials. When heating happens, molecules gain kinetic energy. Okay, so when we apply heat to a material, the molecules vibrate faster. They gain more kinetic energy. Okay, so kinetic energy is directly related to speed. And we see that because of the equation for kinetic energy, which we went through yesterday, which is half mv squared. So we can see that kinetic energy relies on speed. Okay, so if we have a higher kinetic energy, we have a higher speed, and vice versa. So the molecules move faster when we heat them. Now, we know temperature as a value of how hot something is, but now we're going to be taking it one step further in its definition into GCSE level, which says that temperature is the average kinetic energy of the molecules. Okay, so if a material is really hot, the molecules are moving really fast and they have a lot of kinetic energy. So the temperature is hot, it's high. However, on the opposite end of the spectrum, if the molecules are moving slowly, they don't have a lot of kinetic energy and they have a low temperature. Okay, so temperature can now be defined as the average kinetic energy of the molecules. The reason we have the average kinetic energy of the molecules is because they could be vibrating at slightly different speeds. Okay, so that's our new definition for temperature. Now, we know that heating a block of ice is much easier than heating a brick, for example. Okay, but why is this the case? Well, it depends on 3 different factors. So different materials require different amounts of energy to heat up. So it depends on 3 factors, which is the mass of the material, the substance of the material, and the desired temperature change. Okay, which makes sense. A bigger ice block is going to be harder to kind of melt than a smaller ice block. The substance of the material, well, brick is fundamentally harder to melt than ice because of its makeup. So that's what the substance of the material means. And then the desired temperature change. Well, that makes sense. Trying to melt a block of ice by 2 degrees is going to be easier than trying to melt a block of ice by, say, 10 degrees. Okay, so 3 different things that heat energy depends on. And now we're going to relate them all into an equation. So the amount of energy stored or released from a system as its temperature changes is calculated using this equation. So as we change the temperature from, let's say, 5 to 10 degrees, we have a change in the amount of thermal energy. So delta E, remember delta, which you can see here and here, is the triangle, which means change in. So change in something. So for the left-hand side of the equation, it means the change in thermal energy. Okay, so that E is energy, but specifically thermal energy. Okay, not elastic, not gravitational, not kinetic. They all have their own equations. This one is only for thermal energy and only for the change in thermal energy. Okay, notice that it doesn't have a little letter there. It doesn't have a subscript like we're used to. So remember that potential energy, gravitational potential, had EP, elastic had EE, kinetic had EK. This one, they don't tend to put a letter there. So you know that if you see this delta E in this equation, then you know that that means thermal energy. You will be given this equation in the exam for the AQA exam board, so don't worry too much, but you still do need to know what each element means. So we have change in thermal energy. Then we move on to M, which is just mass, and mass is always measured in kilograms, as we know. Then we have C. So C is where it gets a little bit more complicated. C is this new value called the specific heat capacity. Okay, specific heat capacity. That's what C stands for. And it's measured in a more complicated unit, which is joules per kilogram Celsius. Okay, so that's the unit, and you may be asked that in the exam. So you do need to know that. And then we have the temperature change, which is delta theta. So 2 Greek letters there. Delta is obviously the change in. Theta stands for temperature. Okay, so theta is this weird looking letter here, theta, and that stands for temperature. Okay, so the whole thing, delta theta, is the change in temperature. So we have the equation, change in thermal energy equals mass times specific heat capacity times change in temperature. So what is specific heat capacity? Well, specific heat capacity is a value that is independent to that material. So it's that material's value, it never changes for that material. The same with mass, that never changes for that material. So the specific heat capacity is this value that tells us how much energy is required to raise the temperature of 1 kilogram of that material by 1 degree Celsius. Okay, I'll say that again. So let's say we have a brick. Okay, so you can see that brick has a specific heat capacity of 840 joules. Brick, 840 joules. Okay, so that is the specific heat capacity for brick. That doesn't change. So a specific heat capacity of 840 means that it takes 840 joules of heat energy to raise 1 kilogram of brick by 1 degree Celsius. That is the definition of a material's specific heat capacity. Okay, so it takes less energy to raise the temperature of a block of aluminium than it does to raise the same amount of water by the same temperature. Okay, so that means that it's easier to raise the temperature of a block of aluminium than it is to raise the temperature of a block of water, okay, or the same amount of water. So if it is easier to raise the temperature of a block of aluminium, it has a lower specific heat capacity. If it's harder to raise the temperature, it has a higher specific heat capacity, which we can see here. Brick has the highest specific heat capacity. Brick is really hard to warm up. Okay. Then it gets lower and lower as we go through the table. So copper has a lower specific heat capacity, meaning that it's easier to warm up. Same with lead, that's even lower, so it's even easier to warm up by the same amount of the same amount. Okay, so that is really what specific heat capacity is. It is a new concept and completely foreign, and it did used to be in the A level before the GCSEs got changed. So they took it from the A level and put it into the GCSE. So it is definitely one of the more complex ideas that you'll meet in GCSE. So don't worry if you don't get it straight away. We are going to do some questions on it, so hopefully it will make sense, and do ask questions if you have any. Okay, so moving on to power now. Power is the rate at which energy is transferred or work is done. So energy transferred, well, we know what energy transferred is. That's just the energy being transferred from one store to another. Now, the rate at which something is done is that something over time. Okay, that's what rate means. It's taking a quantity and dividing it by time so that we can see how that quantity changes in a certain period of time. Okay, so the rate at which something is done is putting it over time, so dividing it by time. Okay, that will come up a lot in GCSE and certainly in A level, so it is something that is useful to remember. Rate just means something over time. So for power, it's energy transferred over time or work done over time. Okay, now energy transferred and work done are both measured in joules. Okay, so energy is always measured in joules and work done is measured in joules. Power, however, is measured in watts. So a new unit that we've not seen before, power is measured in watts, which is represented by this W. Okay, so a power might be 4 watts. That would be an example of a power rating. Okay, so we could have power equals 4 watts, which is 16 joules divided by 4 seconds. Okay, so the appliance might transfer energy at a rate of 16 joules every 4 seconds, which would give a power of 4 watts. Okay, so we need to be able to compare 2 different motors. Okay, so 2 different motors, 2 different electrical motors, which are used to lift a weight through a vertical height. Okay, so as you can see in our diagram, we have a motor here. Okay, this is our motor. And we have an object attached to the motor. The motor is able to kind of wrap up the string to make the object lift. Okay, that's how the motor works. So we do 2 different motors. We try out 2 different motors in our little mini experiment. The same weight, the same height. Okay, so they're both 2 Newton weights and they're both trying to be lifted by the same amount. So moved up by 10 meters. Okay, we're doing that in both experiments with both motors. When we do this experiment, we find that motor 1 is able to lift the weight in only 5 seconds. But for motor 2, it takes it 10 seconds. Okay, so motor 1 does it in half the time that motor 2 does. Now, stepping back from the maths, let's think about this physically. If motor 1 does it in 5 seconds, but motor 2 takes much longer to do it, motor 1, we say, is more powerful, right? That makes sense. It's like in a car, if a car reaches a speed quicker than another car, we say that the first car is more powerful. We just know that from our physical description of the world around us. But now let's look at the maths and see exactly why this is true using our power equation. So the first thing that we need to work out is work done. So we're going to be using this equation here. However, do note that E and W can be interchanged. So you need to pay attention to which one you can actually work out or which one you're given. Because they could write the equation as P equals E over T, but actually mean P equals W over T. So we need to be wary of that. Okay, so let's compare our motors. The first thing we need to find out is work done. Now, you may or may not know this equation depending on how far you've come in your physics GCSE, but the equation for work done is force times distance. Okay, force times distance. So we know that work done in both scenarios with both motors is force times distance. Well, we have a 2 Newton force and a 10 meter distance. So we know that the work done by the motor, remember, work done is just a force that makes something move. Okay, force that makes something move, and we therefore get 20 joules. So remember, work done is measured in joules. Okay, so now that we've worked out the work done by each motor, we can now put it into our power equation to find out which motor is more powerful. So here you can see that it's E over T, but what we really mean is work done, not energy transferred, work done. So P equals work done over T. Well, work done in both instances is 20. Same force moving through the same distance. But motor 1 does it in 5 seconds, so we divide by 5. Motor 2 does it in 10 seconds, so we divide by 10. Now, when we divide 20 by 5, we get 4. And when we divide 20 by 10, we get 2. So we can see that motor 1 has double the power rating that motor 2 does. So we can therefore say that motor 1 is doubly as powerful as motor 2. Okay, so we need to know how to make this comparison between motors. And it is something that could come up in an exam where you have to compare two different motors using the same force and the same distance, working out work done, and then working out the power rating for each. Okay, so let's move on to our required practical. So we are doing an investigation to determine the specific heat capacity of one or more materials. Okay, so that's the name of the required practical. It's all about investigating the specific heat capacity. Okay, so this is the equipment list that you need for the practical. So I'll just go through each one and why we need it. So for the first bullet point, we have 1 kilogram of copper, 1 kilogram of iron, and 1 kilogram of aluminium, each with 2 holes. Okay, so those are the materials that we're going to be experimenting with. We're going to be trying to find out the specific heat capacity of copper, of iron, and of aluminium. Now we have 1 kilogram because it's much easier to work with. Okay, so putting 1 into our equation is going to be much easier. Now we have 2 holes made in that block. You don't have to make the holes, they'll be there for you before you start the experiment. The reason for those 2 holes is 1 for the heater. So that's this bit here. So you can see that this is the heater here. And the other hole, the smaller hole, is used for the thermometer. Okay. Now we also need a pipette to put water or oil in the thermometer hole. And that is so that the thermometer is insulated and completely surrounded. We have a 30 watts heater. So that's to actually heat up our metal block. A 12 volt power supply to power the heater. We need insulation to wrap around the blocks. So insulation can come in lots of different forms, but the form that they tend to recommend for this required practical is cotton wool. Okay, so we need this cotton wool insulation so that we lose as little heat as possible to the surroundings. By insulating the block, we can keep that heat in. Okay. We also need an ammeter and a voltmeter to measure the current going in and the voltage going in. We need some leads, we need a stopwatch to measure the time, and we need the scales to determine the mass of the blocks, although hopefully it will just be 1 kilogram, but it does depend on what your school give you, and a heat-proof mat to let the block sit on, because you don't want to be touching it when it gets hot. Okay, so the method for our required practical. Well, we need to place the heater into one of the holes at the top of the block. So we saw in our diagram before of the man doing the experiment that he's put the heater into this hole and the thermometer into the other. So that's the first step of the experiment. And then we're going to put a couple of drops of oil or water into the thermometer hole to make sure that the thermometer is completely surrounded by hot material and not air. Then we fully insulate the block by wrapping it loosely with cotton wool. Record the temperature of the block using the thermometer and connect the heater to the power supply and turn it off after 10 minutes. So we're going to record the temperature of the block before we do anything to it, but after we insulate it with cotton wool. Then we're going to turn on our heater, which is connected to the power supply, and we're going to start our stopwatch for 10 minutes. After that 10 minutes is up, the temperature will still rise because of residual heat, and then it will begin to cool. So it will go up, up, up to a point, which is its peak temperature, then it will begin to cool again. So we want to get the highest temperature that that material reaches and calculate the temperature rise during the experiment. So we first recorded an initial temperature of the block before we turned on the heater. That's our initial temperature. Then the highest temperature that it reaches during the experiment, the highest level of the thermometer, that's our final temperature. When we take them away from each other, we get the change in temperature. Now that method is not too bad, probably not one of the harder methods in the GCSE, but what is really the more complicated part of this experiment is the results. So you notice that we take an ammeter reading and a voltmeter reading. Okay, now an ammeter reading and a voltmeter reading might seem really weird in this experiment. Like, why would we do that? Well, actually, we need to do that because we need to get a power. Okay, we need to know the power. So power, you may remember, is IV. Okay, IV. So power equals current times voltage, where our current is 3.65 and our voltage is 10.8. So please, could you put your answers on the chat as to what the power would be in this experiment? So we're doing current, which is 3.65, times voltage, which is 10.8. So what would the power be? A few more seconds to think about that. Cool, loads of you getting the right answer, 39.42 watts. 39.42 watts, great. Okay, so we know the power going through. Now we also know that power equals energy transferred over time. Okay, that's the equation that I just told you. Power equals energy over time. Okay, so we now have a value for power and we also have a value for time. Remember, time was 10 minutes. So we're going to rearrange our equation for energy. Energy equals power times time. Okay, so energy equals 39.42 times time. However, time It's currently in minutes. We need it to be in seconds. So we do 10 minutes times 60, which is 600 seconds. So could you please work out the energy being transferred to the block? So what is the energy? Remember, energy is power times time. So what would the energy be? Cool. 23652. 23 joules. Okay, so now we're switching the units to joules because it's an energy. Previously it was in watts. Okay, so now we have a value for energy. Okay, so the energy transferred from the heater to the block is the change in thermal energy. That's what we've just worked out, the change in thermal energy. Now, going back to the beginning of the session, we had the equation for the change in thermal energy, which was mc delta theta. Okay, so this energy is the change in thermal energy, which now gets put in to this equation so that we can find the specific heat capacity given the change in temperature and the mass of the block. So let's rearrange our equation for specific heat capacity. So we're going to divide both sides by mass. So we get C delta theta on the other side. Then we're going to divide both sides by delta theta. So that we get C on its own. Remember, C is what we're trying to find. We're trying to find the specific heat capacity of that material. Well, now we have every value in that equation, so we can work it out. So we have that the change in energy is 2, 3, 6, 5, 2 joules, divided by mass times the change in temperature. Well, we know that mass is just 1 because it's a 1 kilogram block, and the change in temperature is right up here at the top, 15 to 38. So the change in temperature is 23 degrees. So we can put that in as well. So please, could you work out what the capacity is? So what is the specific heat capacity there? So we're doing 23652 divided by 23. And to get our final answer, the specific heat capacity. Okay, so when we divide 23652 by 23, we get 1028.35. So really good, guys. We've got to the final answer using a lot of equations and a lot of math. So this is probably the hard part of the required practical, is the maths involved with it. Equals C. Great. So we've come up with a value for specific heat capacity from our experiment. First, we found the power by doing current times voltage. And if you need a reminder of how that equation works, then you can go back to the electricity webinar on YouTube. So we found the power. Then we used our new equation, which is power equals energy over time. We rearranged for energy, which gave us energy equals power times time. Now, we already have power because we just worked it out, and we already had time because that was the time that was elapsed in the experiment, which we decided was 10 minutes. This is probably a good amount of time to see a good change in temperature, which is why we suggest 10 minutes. We were then able to find a value for energy. The change in energy equals mass times specific heat capacity times the change in temperature. So we take this energy and we now put it into our second new equation, which is the equation for the change in thermal energy. So we take our change in thermal energy and we divide it by mass and we divide it by the change in temperature, which is what we're doing here. So we take our energy value, 23652, we divide it by the mass times the change in temperature. Our mass is just 1 kilogram because it's a 1 kilogram block, and our change in temperature is 23 from the results table. Dividing all that through gives us our final answer of the specific heat capacity, which is 1028. Now, this experiment has some error attached to it. Okay, this experiment is not perfect by any means. Some heat will be lost to the surroundings. Okay, it's inevitable. No matter how much cotton wool we try to put on top of it, some heat is always going to be lost. Okay, that's just the way heat works. We can't contain it so that it never leaves. Okay, so that's going to become a source of error in this experiment, which might change our results slightly and might end up giving us a specific heat capacity, which is not the correct specific heat capacity of the block. Okay, so the source of error is that some heat will be lost to the surroundings. Okay, so because of that happening, we might get a different value for energy, might get a different change in thermal energy. As well as errors in the ammeter and the voltmeter, but they're kind of less errors, that they're not as important as the heat being lost to the surroundings. Okay, so that is all the content that we needed to cover. We're going to go through some calculations now, because that really is the bulk of this webinar and probably the most important thing, rather than the definitions, which we kind of do with the quickfire questions. So let's have a go at this first equation or question. So Sadie is experimenting with a model steam engine. Before the 0.25 kilogram of water begins to boil, it needs to be heated from 20 degrees up to 100 degrees. If the specific heat capacity of water is 4,180, how much thermal energy is needed to get the water to boiling point? Okay, so a long, wordy question, which is not uncommon in a GCSE. We need to use our equation for thermal energy. Okay, that's what the question is asking us. How much thermal energy is needed? Well, we bring out our trusty specific heat capacity equation, mc delta theta, and they've been pretty nice to us by giving us all the values in that equation. So we won't need to do any rearranging. So we can see that mass is 0.25, which is given. We can see that C, the specific heat capacity, is 4,180 of our substance, which is water. And then we need to do the change in temperature. Well, this is not so clear, but with a simple subtraction, we can work it out. It goes from its initial temperature of 20 degrees to its final temperature of 100 degrees, which is a change of 80 degrees. So our delta theta, our change in temperature, is 80. So could you please put that into your calculators to come up with the change in thermal energy that we have to get it up to boiling point? So remember, boiling point is just 100 degrees, which is what the experiment is doing. So we're doing 0.25 times 4,180 times 80. So we get 83,600. And that is measured in joules. So don't forget to put your units. Energy is measured in joules. Power is the one that's measured in watts. Okay, that's really great. We won't do the next one because it is pretty similar, but we will do the third question. So if I just number them quickly, 1, 2, 3. How hot does a 3.5 kilogram brick get if it's heated from 20 degrees by 20,000 joules? Okay, by 20,000 joules. So how hot does a 3.5 kilogram brick get if it's heated from 20 degrees by 20,000 joules? Well, this requires us to use the specific heat capacity of brick, but we'll put in the rest of our values first. So delta E equals mc delta theta. Now we want to know how hot the brick gets, so we need to get delta theta on its own. So let's rearrange our equation and divide both sides by mc so that we're left with delta theta. Now we have everything we need, 20,000, which is given. Yeah, so 20,000 is given in the question. The mass, 3.5, is also given in the question. And the specific heat capacity of brick is 840, I believe. Yeah, 840. Which gives us our change in temperature. So could you please plug that into your calculators and come up with a value for the change in temperature? So we're doing 20,000 divided by 3.5 times 840. You might like to do the multiplication first and then do 20,000 divided by that answer. Give you a few more seconds for some more people to work that out. So 840 is the specific heat capacity of brick. That's just a value that never changes for brick. Okay, so when we put that through, we get 6.8 as our change in temperature. So remember, this is a change in temperature. So if it's starting from 20 degrees, we want how hot does it get? So we want the final temperature. So if it starts from 20 and the change in temperature is 6.8, the final temperature is 26.8. Okay, so it raises the temperature by 6.8 degrees. Okay, and then we'll finally do this last one before we go on to your guys' questions. So a hairdryer transfers 48,000 joules of energy in 1 minute. What is the power rating of the hairdryer? Well, remember, power equals E over T, where E has been given, which is 48,000, and T has also been given, which is 1 minute. We never work in minutes, we always work in seconds, so minutes changes to seconds. 1 minute is 60 seconds. So please, could you work out the power rating for the hairdryer? 48,000 divided by 60 is 800 watts. So the power rating of the hairdryer is 800 watts. Okay, so we're going to stop there, and I'm going to take some of your guys' questions. Okay, so someone said, what's EP, what's EK? EP is gravitational potential energy, and EK is kinetic energy. If you want to know more about them, then go to the webinar that we did yesterday, and I will tell you in loads of depth. Do they give you the equations in the exams? They give you some. They tend to give you the more complicated equations. So they do give you elastic energy, and they do give you thermal energy, but they don't give you potential energy, and they don't give you kinetic. So I would suggest that you go to your syllabus, so type in GCSE, your exam board, so AQA, EdXL, whatever it is, physics, equation sheet, probably be the first link. Go and have a look, see what they give you, and so you know which ones you don't need to learn. I say you don't need to learn, you do need to learn them, but you don't need to memorize them. So you do need to know what each part of the equation is, because they won't tell you that. They'll just give you the letters and the symbols, which sometimes aren't that easy to work out what they're talking about. Is it more likely for AQA exam board to ask the method or calculating the result? It's much more likely for them to ask you to calculate the result, just because it is quite a complicated multi-step problem. In slide 11, why is that E the change in energy? Okay, so the change in energy comes from, well, this experiment takes electrical energy and it changes it into thermal energy. So this is the electrical energy, which gets changed into thermal energy. Okay, so the electrical energy comes from current and voltage divided by times by time. So that is electrical energy, which then gets transferred into thermal energy, which is why we can put this value of energy into our thermal energy equation. Even though they're two types of energy, we say that all of the electrical energy gets transferred into heat energy. But again, another source of error, realistically, not all of that electrical energy goes to heat energy. Some of it will get lost in the wires, in the grips, or whatever. Okay, so some of the energy will inevitably get lost. So all of that electrical energy does not necessarily go to all of the thermal energy. So another source of error that we have. Specific heat capacity can be measured in joules, kilograms, or degrees Celsius. But how do you determine which one you measure in? Okay, so that might have confused you a little bit, because in the table it has joules per kilogram per degree Celsius. So they're not slashes. That doesn't mean pick one of the three. That is genuinely the units that they're in. So I'll do a quick little derivation for you to show you that they are the units. So delta E is mc delta theta. Okay, so let's first of all take the units of each of those elements of the equation. We know that E is measured in joules. We know that mass is measured in kilograms. And we know that specific heat capacity, well, we don't know, that's what we're trying to work out. And we know that delta theta is degrees Celsius. Okay, so now let's rearrange that equation for C. So we divide both sides by kilograms, and then we divide by degrees Celsius, so that we get C on its own. So we can see that specific heat capacity C is measured in joules per kilogram per degree Celsius. So they're not slashes, it's really joules divided by kilograms divided by Celsius. So the amount of joules needed per kilogram per degree. Can this topic be found in the Edexcel exam board? Yes, and is AQA the hardest exam board? I wouldn't say any exam board is really harder than the other just because they overlap so much. One exam board might have a topic that another exam board doesn't, and it might be a harder topic, but they kind of all balance out, to be honest. I wouldn't say that one's harder than the other. They couldn't really do that because that'd be really unfair to students. What is the unit for the change in thermal energy? Is it joules? Yes, the change in thermal energy is joules. Any energy is joules. EP, EK, EE, thermal energy, all joules, any type of energy. Power is watts. I think that might be all the questions. How did you get the 840? Still not sure. So 840 is the specific heat capacity of brick. Okay, so specific heat capacity is a value that is specific to that material. So brick has 840, water has 4,180, and steel has 450. So they each have their own kind of specific heat capacities. Just so happens that specific heat capacity for brick is 840. But you will always, always, always be given the specific heat capacity if you're expected to use it. So you don't need to remember specific heat capacities for lots of different materials. Okay, I think that's all the questions.
Yeah, it looks like that's all the questions that I can see, but if you guys have any more, do pop them in the chat in the last few minutes.
Is AQA the one that most schools pick for physics? It does tend to be the more common one, but there are an equal amount of resources for all the exam boards. Just because I base my webinars on the AQA exam board, that doesn't mean it's better or easier or harder. It's just the one that we've chosen to do. Okay. I'm not sure you heard my answer, but basically someone keeps asking what is more possible for the AQA exam board to ask, the method or calculating the result. They're more likely to ask you to calculate the result because it's a multi-step problem and it is quite a complicated problem. The method is probably going to be a 6-mark question if they do ask it. Do you have any tips for exams in terms of remembering all the information? Okay. So for remembering all the information you need to know in physics, you're quite lucky because physics is not so much remembering. It's more half remembering, half maths and graphs and tables. However, biology and chemistry tend to be more remembering. So first of all, we're quite lucky in the sense that physics is not so much that. But what you do need to remember is definitions and certain equations. So the ways that I tend to remember physics and the things that I need to remember is I'm a visual learner, so I make posters, I do it in nice colours, and actually in an exam I remember where things were on the paper to help me remember content that I needed to know. So it really depends on what kind of learner you are. I know that sounds really cliche and your teachers probably shove that down your throat all the time, but it is really important that you work out as soon as possible how you remember things in the exam. So not necessarily what type of learner you are, but in an exam, how do you recall that equation? Do you remember seeing it on your wall on a pretty poster? Do you remember your teacher saying it to you or me saying it to you? Or do you remember doing the practical? Okay, so how do you remember things in an exam? That's going to help you know how to revise. So whether you need to make posters, make mind maps, but yeah, as I said, there are two parts to physics: the calculations, the numerical, and the qualitative. So it's important that you put an emphasis on both. Is it hard for year 11 to transform to sixth form to study physics? How can I prepare? Okay, so I did the switch from GCSE to sixth form studying physics. A-level physics is obviously harder, it always will be, but I wouldn't say that the transfer is really that hard, because what they've done is they've changed GCSE. So they changed GCSEs in 2016, but they kept their A-levels the same. But what the GCSE people did is take some content from the A-level and put it into the GCSE. So this whole thing about equals MC delta theta is taken from the A-level. So they've done that to make the transition much easier for you. So I would say that it's definitely easier now than it was before. Things that you can do to prepare is, I wouldn't say kind of start reading the A-level content. That wouldn't be necessary. But what I would say is start thinking about the why more. So with GCSE, it's very easy to just recall, learn the methods that your teacher taught you, learn the ways to answer the questions, and that's it. But if you really want to take it that step further into A-level, then learning about the why, so why does this happen, is really important. And how can I apply my knowledge into different situations? Is GCSE just as hard as people make it seem? That really differs for every subject and every single person. Some people find physics harder, some people find English harder. I really can't say, but I would say is just work hard. If you do need the help, you know where to get it, the webinars. My tutor has loads of resources for you. But yeah, don't stress too much. It's really just as hard as you make it. If you put the work in, then you'll get hopefully the results that you want. So just try your best. Okay, so I think that's all the questions, and we're just about to finish the webinar.
Brilliant, thanks Preshayla, and some great questions there, guys. Thank you so much. Thanks for joining us today. We have some other group tutorials today, as you probably know, in some other subjects. If you wanted to join us for those, we have English, Maths and Biology today. But if you just join us for physics, then the next physics session is this Wednesday at 2 p.m. So hopefully see you lot there, unless you're coming to any of our other sessions today. Thanks so much, Preshayla, for today's lesson. And later today, guys, you can find this lesson uploaded to YouTube if you wanted to just check over anything or jot down some notes from anything earlier in the session. So have a lovely afternoon, everyone, and see you soon. Bye.
Thank you. Bye.